Hello everyone and welcome back to Math Made Easy. In our previous lecture, we started the bisection method, one of the most reliable techniques for finding the roots of nonlinear equations. And we learned that by repeatedly dividing an interval in two equal halves, we can approximate the root with any desired level of accuracy. Although the bisection method is simple and it guarantees convergence whenever its conditions are satisfied, it has one important drawback as well, that it converges slowly. But this naturally raises an important question: can we choose a better approximation than the midpoint? If the graph of the function is itself providing you more information, why not use that information instead of simply taking that middle point? So the answer leads us to today's topic, the regular falsi method, and also known as the false position method. So if I just draw a curve and mark the endpoints and the midpoint as well. So in the bisection method, we can always choose the midpoint of the interval. So is that midpoint always close to the actual root? The answer is not necessarily. Now if I draw another curve with these endpoints, so suppose the graph is actually bending sharply towards one endpoint. And even though the middle point lies exactly halfway between the endpoints, the actual root may be much closer to only one side. So instead of selecting the midpoint, let's just try something more intelligent. We can have these endpoints, so we can define a function over that endpoints, and we got these 2 points. And if I just draw a straight line that joins this AFA point to BFB point, the straight line becomes the secant line. And if we just extend it until it increases, and if we extend it until it intersects the x-axis, that intersection gives us another approximation to the root. Since this approximation uses the values of the function itself, it is often much closer to the actual root than the midpoint. And it is the central idea behind this regular falsi method. And basically this term regular falsi comes from the Latin and literally means rule of false position. The point that obtained from the second line is known as the false point or false position because it is not the exact root. It is simply an approximation. And as the iterations continue, this approximation becomes increasingly accurate. So we just begin with a continuous function here that satisfies the f of a and f of b is lesser than 0. Therefore, by the intermediate value theorem, at least one root lies within that interval. So instead of taking the midpoint, we draw the secant line joining the endpoints. And the x-intercept of this secant becomes our next approximation. So here, notice that the secant line is influenced by the shape of the function. And that is why the regular falsi method usually converges faster than the bisection method. Now comes the derivation part. Most of the students memorize the regular falsi formula. So instead, let's just understand where it comes from. So if I just draw the two endpoints, and hence the two endpoints of the function gives you the equation of the line that passes through this AFA and BFB. Then forming an equation of the line, we got this. We got this y minus fa divided by x minus a equals to fb minus fa divided by b minus a. Since the root lies on the x-axis, therefore this y should be 0. So just substituting here, we got this minus fa divided by x minus a equals to fb minus fa divided by b minus a. Just cross multiplying and then expanding and then collecting the x terms, we finally obtain this x equals to afb minus bf of a divided by f of b minus f of a. You don't need to memorize this formula anymore. If you remember the equation of a straight line, you can derive it whenever required. Now comes the algorithm part. So there will be few of steps, out of which the first step says you need to just choose the endpoints, that is this A and B, such that this FA and FB is lesser than 0. Now computing the value of C, which is basically over the iteration formula. That is C equals to AFB minus BFA divided by FB minus FA, and hence evaluating the value for FC. So if that value becomes 0, the root has been found. Otherwise, if it is not 0, then two cases arises, out of which first one will be either FA, FC is lesser than 0, then you need to replace B equals to C. Then the new interval will be A to C. Else, you got this FB, FC lesser than 0. Then you need to replace A equals to C. Then the new interval becomes C to B. And you need to repeat until the stopping criteria is satisfied. Now comes the question that asks for the root of e to the power minus x by using the Regula Falsi method in the interval 0, 1. So we have defined the function so well. Then we got the endpoints as 0 and 1. So we need to define a function over 0 and 1 as well, where this f0 becomes 1 and this f1 value is minus 0.632121. And since this f0 and f1 is lesser than 0, then 100% this root lies in 0, 1. Now using the Regula Falsi formula, we got the C equals to AFB minus BFA divided by FB minus FA, where we are having this A equals to 0 and B equals to 1, and hence this FA equals to 1 and FB equals to minus 0.632121. And using the Regula Falsi iteration formula, we get the C1 value as 0.6127. And then computing the function value over this point, we get this e to the power minus 0.6127 minus 0.6127. And hence we got the value as minus 0.0708. So we need to replace the B value, and the newest interval becomes this 0 to 0.6127. And with the second iteration, we have the interval as 0, 0.6127, where we have the value for f of A and f of B as well. Then computing the value for the C, which comes out to be as 0.5722, and the function value becomes minus 0.0079. Therefore, the new interval becomes 0 to 0.5722. And continuing this way, we got the iteration table as follows, where we got the final root of the equation e to the power minus x equals to 0, that is this 0.5671. And basically this value is known as to be the omega constant, that actually satisfying the x equals to e to the power minus x. So basically, this is having the advantage over the bisection method because that uses the shape of the function and it hence works faster than the bisection method since no derivatives are required and actually maintains the bracketing property. But there is a drawback as well that only one endpoint may remain fixed for many iterations and still having the linear convergence, and the performance is depending upon the function only. So basically, both the bisection method and the regular falsi method are bracketing methods, but still the regular falsi method makes better use of the function's behavior by replacing the midpoint with the x-intercept of the secant line. So today we learned how the regular falsi method improves upon the bisection method by using the equation of a straight line to obtain a better approximation to the root. We explored its geometric interpretation, derived its iterative formula, understood its algorithm, and solved a complete numerical example stepwise. As we continue this course, you will notice that each new method is designed to improve either the speed, accuracy, or the efficiency of finding roots, while building on the concept we have already learned. In next lecture, we'll study the Newton-Raphson method, one of the most powerful root finding technique, and we will derive its iterative formula using tangent lines and understand why it converges much more rapidly than the methods we have studied so far. Thank you so much for watching. If you found this lecture helpful, don't forget to like and share it to your classmates and subscribe to Math Made Easy. And I'll see you in the next lecture.